Welcome to this MOOC on lasers. In this lecture, today we will see laser rate equations in a 3-level system. A very quick recap that in the last class, we discussed about 2-level, 3-level and 4-level systems. In particular, in 2-level systems, we saw that population inversion cannot be achieved in steady state even by external pumping. And then we saw that the 2-level system would in general act like an absorber, and we also discussed about saturable absorbers. So, today we will take the 3-level systems, write down the laser rate equations and then find out the condition under which amplification by stimulated emission is possible. Okay. So, a very quick recap of what is the 3-level atomic system. So, basically the 3 levels which participate in the interaction are the ground state and 2 excited states or the upper levels. N1, N2, N3 are the population in these levels, and the possible transitions we have shown that from ground state we can have absorption go to the 3rd level, and then the atoms can come down directly to level 1, or they could also come down to level 2 and then come down to the ground level. Any other transition we have neglected in this. Now, h nu p is the energy of the pump photons and h nu l is the energy of photons corresponding to the transition from 2 to level 2 to level 1. So, what we have discussed is it is possible to have population inversion between level 2 and level 3 if we pump sufficiently fast to this upper level, and if the atoms come down rapidly to the level 2 and then they get stuck or wait here for a longer time. In other words, if this level 2 has a longer lifetime, if this has a longer lifetime, then it is possible that the atoms will lifetime, then the atoms can accumulate in level 2 and soon they can become more than the number of atoms in the ground state N1 and population inversion can be achieved. So, we will write the rate equations for this system and see what is the method, whether this condition is correct or not. All right. So, before we write the rate equation, the system that we are discussing is typical of a ruby laser. A ruby laser is a 3-level system, but the actual levels of ruby are shown here. So, this is the ground state. So, ground, and there are 2 bands which are shown here, 4F1 and 4F2 at the excited level, which correspond to wavelength. So, these are approximately 50 nanometer wide. The energy delta E corresponds to it is not delta E of about 50 nanometer. So, they are 2 absorption bands. Therefore, green light around 550 nanometer will be absorbed, will excite atoms from this ground state here, from the ground state to the 4F2 level, and blue light around 400 nanometer wavelength will excite atoms to the upper state. These atoms rapidly come down to 2 intermediate states which are called R1 and R2. These are traditional nomenclatures of R1 and R2. The level R1 and R2 have a long lifetime, typically about 3 millisecond in the case of ruby. Ruby is chromium doped alumina. It is a chromium doped alumina crystal which has levels. So, these levels which have long lifetime are called metastable states. So, metastable states, levels or states, metastable states. So, whenever you have energy levels which have a long lifetime, atoms can accumulate there. So, what is happening is atoms are excited to a higher energy bands 4f1 and 4f2. Usually they use a xenon flash lamp. So, Xc flash lamp is used to excite these atoms. We will discuss Ruby laser when we discuss about the laser systems towards the end of this course, but right now a very quick outline of this Ruby laser just to show that this is a 3 level system. There are several levels participating. 4f1 and 4f2 are the excitation bands, that is atoms, if they are excited to these bands, they rapidly come down to levels R1 and R2. So, these are rapid non-radiative transitions, very fast non-radiative transitions. But the transition from level R1 and R2 are slow, and that is why the lifetime of the level is of the order of 3 milliseconds. And this transition gives down 2 lines, the 694.3. So, this is 694.3 nanometer is the predominant line of the Ruby laser, and this is 692.9, which is about 693 nanometer, is less dominant. So, this is the Ruby laser line, which is the dominant laser line. Now, the important point to note is the role of these two bands, is to populate the metastable level through the excitation mechanism. In other words, essentially, let me change the color here. So, essentially atoms are excited to this level or this band, and then from there they come down here. In other words, the band helps in populating this, because if we were to pump atoms directly from here to here, they will come down with the same probability, and therefore, we can never achieve, we have already seen in a 2 level system we cannot achieve population inversion. However, if we pump atoms from ground state to a third level or a third band or a multiplicity of levels, from where atoms rapidly come down to an intermediate level, then we can have inversion, population inversion between this intermediate level and the ground state. And therefore, an equivalent 3 level diagram is shown here. So, the upper excitation here, upper level is actually the combined bands which are shown here. So, there is a third level, atoms are excited to the third level, from where they come down to the second level where population inversion can take place. So, right now I have not shown population inversion, but population inversion can take place, and the transitions which are shown are the predominant transitions, in the sense atoms are absorbed to this higher excited level or multiplicity of levels, from where they come down rapidly to the second level, and from there this second level could also be a multiplicity of levels, from there it comes down to the ground state. And again, just to repeat, that if the second level here, intermediate level, has a long lifetime or it becomes a metastable state, then atoms can get accumulated here and create population inversion, which is the necessary condition for amplification by stimulated emission. With this picture in mind, let us write down the rate equations. Okay, rate equations for a 3 level system. So, for a 3 level system in the presence of a pump, so this is the pump, a pump which is exciting atoms from the ground state to the third level. The rate equations are, first we are writing dN3 by dt. So, if N3 is the number of atoms in level 3, N2 is the number of atoms here, and N1 is the number of atoms, then dN3 by dt tells us the rate of change of population in level 3, that is N3. Now, N3 would increase because of an absorption Wp times N1. So, this is absorption, Wp is the pumping rate per atom, per, and therefore, Wp into N1 will tell us the number of atoms excited to the upper state per unit time per unit volume. Now, the same Wp will also bring down atoms here by stimulated emission, and therefore, we also have, so Wp into N1 will increase dN3 by dt, that is N3 will increase, and Wp into N3 is the atoms coming down here, and therefore, it is negative, it will reduce N3, and that is why we have here minus N3 term, Wp times minus N3. What other transitions? There is T32 into N3. So, T32 into N3. So, atoms which are spontaneous transitions, in this case it is primarily non-radiative transitions. So, NR here referring to the non-radiative transition. So, T32 into N3, and one more term, atoms could also come down here, oh it is written here. So, T31 into N3, atoms from here could spontaneously come down here or spontaneously come down here. They may come down by stimulated emission, which is Wp into N3. So, these are the only possible transitions as far as level 3 is concerned. So, we have taken care of all the 4 terms. So, 1, 2, 3 and 4 transitions. Now, let us look at dN2 by dt, that is rate of change of N2 at level 2 here. So, at level 2 you can see there is transition coming from level 3, and from level 2 there is stimulated emission, spontaneous emission, and then absorption, and therefore, we have 4 transitions here as well, and therefore, we have 4 terms as before, WL into N1, that is this one, absorption, the one which is going up here, WL into N1 will increase N2, therefore, it is positive number. WL into N2 will come down, and therefore, it is a negative minus, and then T32 into N3 will add atoms to level 2, and therefore, it is positive N3 times T32 and minus N2 times T21, because from T21 atoms are coming from level 2, the T21 transition will bring down atoms, which means there is a loss of atoms at level 2, and therefore, it is a negative sign, and therefore, this is for this level. And what about the last level N1? So, the rate of change dN1 by dt will be equal to, you will see that there are 6 transitions here, therefore, 6 terms will be there, Wp into N3, atoms coming down from here, then atoms coming down by spontaneous emission, stimulated emission, atoms coming down by spontaneous emission, stimulated. So, 4 positive terms, spontaneous, stimulated and stimulated, and then 2 negative terms which are absorption. So, one going up here and one going up here. So, 2 negative terms, there are 6 terms. So, these are the rate equations which describe the rate of change of population of levels 1, 2 and 3. So, that is why these are called rate equations for a 3 level system. All right. So, now let us pick up the first one here dN3 by dt, and at steady state each one of them must be equal to 0. So, at steady state maybe it is written in the next page, at steady state each one of these equal to 0, that is dN3 by dt equal to 0, dN2 by dt equal to 0 and dN1 by dt equal to 0. All right. So, let us use the first equation here dN3 by dt equal to 0. So, this term here is equal to 0. So, if we put that equal to 0, then we can simplify this dN3 equal to 0. So, we take N3 terms to one side, that will leave N1 only here. So, we have N3 into, when this goes to the other side. So, N3 into T31 plus T32 plus Wp. So, we have N3 into T31 plus T32 plus Wp equal to Wp into N1. That is the first term, and therefore, N3 by N1 is equal to Wp divided by Wp plus T31 plus T32. Similarly, the second term dN2 by second equation dN2 by dt equal to 0 gives us. So, we can write, take the N2 terms together and N3 terms together, and then we can write N2 by N1 into WL plus T21 is equal to WL plus T32 into this. Now, N3 by N1 we have already got the expression here. Therefore, that is equal to WL plus T32, and for N3 by N1 we substitute for 1, which is Wp divided by this. So, which comes out, therefore, N2 by N1, this term goes to the other side and you have WL divided by WL plus T21, this term here, plus Wp into T32 divided by, so Wp into T32 divided by this term into the other term. So, this is equation number 2. So, we have got expression for N3 by N1 and N2 by N1. Now, recall that N1, N is the total number of atoms. So, total number of atoms will be equal to N1 plus N2 plus N3. So, if we take out N1, so N1 into 1 plus N2 by N1 plus N3 by N1. So, we have expressions for N2 by N1 and N3 by N1, equation 1 and 2, and therefore, N1 is equal to N, total number of atoms, divided by the terms in the bracket. So, this is equation 3, very simple algebra. So, let us continue further, and therefore, now N2 by N1 minus 1 is equal to N2 minus N1 by N1. Therefore, N2 minus N1, why are we interested in N2 minus N1? Because we want to get population inversion, which means N2 should be greater than N1. Therefore, if we call N2 minus N1 as delta N, then N2 minus N1 is equal to N1 into, so this is N1, the whole thing here is N1. So, this is N1. So, N1 into N2 by N1 minus 1. So, minus 1 is here and this expression is N2 by N1. Please see the equation, previous equation. So, N2 by N1 is this expression here. So, we can have a common denominator and then we can get this expression. So, this is N1, and up to this we have made no approximation at all. Now, we want to see, typically instead of keeping all the terms, some practical approximations can be made. In general, in all the subsequent derivations as well, we will try to simplify the expressions by applying practical approximations. If we have some number which is very big, which is being added by a small number, it makes hardly any difference. But mathematically, if you want to do rigorously, you have to keep all the terms, which makes finally at the end of the calculation maybe less than 1% difference. And therefore, we will make these practical approximations as and when they are relevant in obtaining simple analytical forms. So, now let us look at the typical numbers T32, that is that non-radiative transitions. If we recall the picture here, the 3 level system. So, you have this pump and this is T32 and this is T21. So, this is T21, this is T32. For practical systems, we know that this non-radiative transition is very fast. Typically, T32, the numbers are 10 to the power of 8 to 10 power 9 per second. And T31, that is the transition which is coming from level 3 to 1. So, this is 1, level 2 and level 3. So, T31 is typically 10 to the power of 5 to 10 to the power of 6 per second, and T21 is the slowest, because for metastable states we are looking at practical laser amplifiers where there is a metastable state which helps us in creating population inversion. So, typically T21 is of this order. Let us take some practical examples. T21 is 1 divided by tau L is the lifetime. In the case of Nd:YAG laser, tau L is approximately equal to 200 or 230 microsecond. In the case of ruby, the lifetime is of the order of 3 millisecond. In the case of erbium doped silica, we will see this later, erbium doped silica optical fiber amplifiers, where the lifetime tau L of level 2 is of the order of 10 milliseconds. 10 milliseconds is 10 to the power of minus 2 seconds, and therefore, 1 by tau L is equal to 10 to the power of 2 second inverse. So, that is what we have written here. T21 is of the order of 10 power 2 or to 10 power 4 second inverse. The point to note is T21 is much smaller compared to T32 and T31. So, therefore, using the approximation, T32 is much greater than T31. For example, here there are 2 orders of difference typically is much greater than T31, which means we are neglecting this term T31 here and here. In comparison to T32, we neglect T31. Then the expression simplifies to this expression here, Wp N2 minus N1 by N. Please see there is a minus 1 here, from where these negative signs have come. So, Wp into T32 minus T21, this is the only. So, we have neglected T31 comparison to T32, and then you simply simplify, show this, that N2 minus N1 by N is equal to this expression, expression number 4. From this we see that for N2 minus N1 to be greater than 0, that is to achieve population inversion. Please see, N2 is the number of atoms here, N1 is the number of atoms here, and N3 is the number of atoms. So, N2 greater than N1 means there is population inversion. To achieve population inversion, the numerator must be greater than 0. So, this numerator here must be greater than 0 for population inversion. So, let me write as Pi. So, that is what is written here, Wp into T32 minus T21 is much greater than this. This implies first condition, T32 must be greater than T21. What was this T32 and T21? Look at this, this is T21, rate at which atoms coming, and T32. T32 has to be greater than T21. So, that is what we discussed even before we wrote the mathematics. So, when we discussed here, even before we wrote the mathematics, we said that if this rate is slower compared to this rate, then accumulation can take place at this level. So, now mathematically we have got this expression that T32 must be greater than T21. So, naturally T21 should be as small as possible, which means 1 by T21, which is tau L lifetime, must be as large as possible, or we need a metastable state. Since T32 is much greater, the requirement is T3 should be greater than T21, but we know that T32 is much greater than T21. Again go back to see the practical numbers, T32 is of the order of 10 power 8, 10 power 9, and T21 is of the order of this in practical laser systems, and therefore, we have T32 much greater than T21. Then we can neglect. So, in this expression, look back, if T32 is much greater than T21, so T21 can be neglected here, and then we have Wp into T32 minus T32 into T21. So, T32 comes out and we have Wp minus T21 into T32. So, that is what is written here, Wp minus T21 into T32 in the numerator, and denominator is written here. Now, therefore, to have gain, we need N2 greater than N1, which implies Wp must be greater than T21. What is Wp? Wp is the pumping rate per atom, and when Wp equal to T21, we have N2 equal to N1 or N2 minus N1 equal to 0. So, N2 minus N1 equal to 0 is called the threshold for amplification. It is the threshold for amplification. Why is it called threshold? Because N2 minus N1 equal to 0 implies there is no population inversion, but any additional atoms N2 in the level will make N2 minus N1 greater than 0, and suddenly amplification will start. And therefore, the value Wp equal to T21 is called the threshold pumping rate. So, W, and we add this small subscript T to indicate that it is the threshold value. The threshold pumping rate is simply equal to T21. What is T21? 1 by lifetime, and lifetime tau L is a measurable quantity. Tau L can be measured in practice, and therefore, you know the value of T21. If you know the value of T21, you know what is the threshold pumping rate which is required before amplification starts. So, you know the pumping rate required to start amplification. Now, once we know the pumping rate, then we can calculate what is the power, because in practice we would require to know the pumping power, and we will see how to calculate the practical pumping power in watts or kilowatts or whatever. So, units, that what is that number rather than just writing Wp. Okay. All right. So, finally, therefore, the scheme of 3 level amplification is summarized here. You have a pump of energy h nu p, which is raising, that is, which is exciting atoms from the ground state to level 3, and from level 3 they come down rapidly. Therefore, you can see the steady state number in N3 is very small, and therefore, numbers are the number of atoms shown qualitatively is very small. And because T21 is small, the spontaneous transition rate from here to here is very small compared to T32, atoms will start accumulating here. T21 is small means what? The lifetime is larger. Lifetime is larger means what? Atoms will accumulate here. Atoms take the average time taken by atoms to make a downward transition or to get de-excited is large, and therefore, we have accumulation taking place here, and soon it is possible, if you pump sufficiently hard so that your pumping rate is greater than T21, then it is possible to have N2 greater than N1 or population inversion, which implies population inversion. So, when population inversion takes place, the system can provide amplification by stimulated emission. Amplification to which radiation? The radiation corresponding to this gap, radiation corresponding to this energy difference, because any incident radiation, which we call as h nu L, L standing for laser subscript, radiation h nu L corresponding to this energy difference will get amplified by stimulated emission, coherent amplification by stimulated emission. So, this is the pump causing a population inversion, which results in amplification of the signal or the laser radiation, which corresponds to the energy difference here. This is the principle of operation of a 3 level amplifier, a scheme of amplification of a 3 level system. Okay. Let us discuss something more, an important concept of gain saturation. Now, recall equation 5 is the same equation I have rewritten. So, equation 5 which is here in this page here. So, this is equation 5. So, it is rewritten here, recall. In this equation, if you see, if we divide the denominator and the numerator by this term T32 into WP plus T21, then what in the numerator, of course, T32 cancels and we have WP. So, the expression is written here. So, this is the same expression where we have divided by this first term to all the 3 terms. If we look at this last term, T32 is 1 by T32 is in the denominator and T21 is much smaller than T32. WP is almost of the same order as T21 because the threshold value is WPT equal to T21. And in practical systems, WP will be slightly greater than WPT if you want to get amplification, because this is the threshold value WPT. So, WP pumping rate must be greater than WPT, which is equal to T21 for amplification, but in general WP is of the order of T21 and therefore WP is of the order of T21, but T32 is much bigger compared to this number and therefore, this number is the third term here in the denominator is negligible. So, we neglect this term and then we can write delta n as what you have in the numerator plus 1 plus WL into all of this, WL into all of this. So, this we call as tau s, say tau s. If we call this as tau s, tau is a unit of time, you can see that it is unit of time because this is time, inverse time, inverse time, inverse time, inverse time. So, this cancels, but there is another inverse time, therefore, it goes to the numerator which must be time and therefore, we call this as, so we say that let this be tau s, then we can write delta n nearly equal to this. We have neglected the third term, that is why this nearly equal to sign WP minus T21 divided by this, where tau s is equal to the term which is within the circle. So, note that T32 is much greater than T21 and this we have already discussed, typical numbers are here and therefore, this term was neglected. So, the term last term was neglected and we have an expression for delta n here. We will take it further and discuss it in the next. So, here delta n is equal to, this is what we had written there, and tau s using WL is equal to, WL is I nu into sigma of nu, the cross section divided by h nu. This we have derived earlier in the definition of WL. And Is, if we define Is as h nu divided by sigma of nu into tau s, then we can write delta n is equal to delta n 0. So, we call everything on this numerator as delta n 0 and WL into tau s. So, WL is here. So, WL into tau s here. So, maybe I can write here WL into tau s in the denominator is equal to, this is the definition of WL, sigma of nu into h nu into tau s here. Now, what we are saying is leaving I nu, if you take these 3 terms together and call this as 1 by Is or Is is equal to, as defined there, h nu. So, Is, so this term is 1 by Is, 1 by Is. If we define this as 1 by Is or Is is equal to h nu by sigma of nu into tau s, then we can write this as delta n is equal to delta n 0 into 1 plus I nu by Is. So, we have called this quantity as Is, S standing for saturation intensity. Why we are calling it as saturation intensity? We will see in a minute. And what is delta n 0? Delta n 0 is everything which was in the numerator, that was here. So, this was delta n 0. Note that delta n 0 does not contain I nu, or delta n 0 is independent of I nu. I nu is what? I nu is the intensity of the radiation passing through that medium or atomic system, and Is is called saturation intensity. Why it is called, we will see in a minute. So, delta n is equal to this. We have got an expression where delta n is intensity dependent, delta n 0 is not dependent on the intensity, it depends only on the pumping rate. Delta n 0 depends on Wp, pumping rate. If you change the pumping rate, delta n 0 changes. T21 is the characteristic of the given medium, it is characteristic of the medium because it is the inverse of lifetime, and therefore, gamma of nu, that is the gain coefficient. So, this is the gain coefficient. So, gain coefficient gamma of nu is equal to sigma of nu into delta n. We have already derived this, and sigma n into, now we are substituting for delta n 0 divided by this. And if we call this numerator sigma of nu into delta n 0, this independent of intensity, as gamma 0 of nu, then gamma of nu can be written as gamma 0 of nu divided by 1 plus I nu by I s, where I s is called the where this expression is called the saturated gain coefficient. I s is the saturation intensity, but this expression is called the saturated gain coefficient. Why it is called saturated gain coefficient? We can see that the gain coefficient is a function of intensity of the radiation. So, here is a plot which is showing the variation of gamma of nu with I nu. As you can see, when I nu is equal to I s, which is the saturation intensity, the term will become 1 or the gain drops to half of its value. That is the definition of saturation intensity. So, one can measure this saturation intensity by observing that the intensity of the radiation passing through the medium. So, what we are saying is this. So, you have a medium which is a gain medium. When light intensity passes through this, you get an amplified output. So, if I can show it as a small sinusoid with the small amplitude, then after amplification you get an amplified output here. Depending on the, this is I nu, intensity of the radiation which is entering, and then of course, inside also it is I nu, but I nu will go on increasing. But if I nu remains small compared to, even when it comes out here is small compared to the saturation intensity, then the gain coefficient, if I nu is much smaller than I s, then gamma of nu is equal to the small signal gain coefficient gamma 0 of nu for I nu much less than I s. So, that in the denominator the second term can be neglected, and this is called the small signal gain coefficient. Small signal because the intensity I nu is small. When this is small, this means this is small. When the intensity is small, then the gain experienced is gamma 0 of nu, which is called the small signal gain coefficient. Whereas, as the intensity increases, then we will have the saturated gain coefficient. In other words, as intensity increases, the gain coefficient drops down as shown in the diagram which is here. And for large intensity, literally the gain coefficient comes down to 0. Gain coefficient comes down to 0 means what? We have I nu of z at any intensity is equal to I 0 at the input into e to the power of plus gamma times z. If gamma becomes 0, that means output will be equal to input. Let us discuss this as an application in, it is more clearly illustrated here, small signal amplification. If we have a weak input signal passing through the gain medium, so this is the gain medium, so gain, which provides a gain coefficient gamma 0 of nu, then the input I0 will exponentially get amplified, exponentially it will build up by this expression I of z, that at any z here starting from z equal to 0, z equal to 0 is this point input, and z equal to L because length of the gain medium is L. So, from z equal to 0 to z equal to L, the intensity will build up exponentially by this formula, provided the signal intensity for I nu of z at any value of I nu is much less than the saturation intensity, and this we call small signal amplification. But what if there is saturation, that is we have a small signal which is incident, after as it passes through the medium it is getting amplified, but if the intensity becomes larger then the gain coefficient will drop down, and therefore, the intensity will initially build exponentially and then it will slow down and then it will almost saturate. That is why it is called gain saturation. The intensity variation through a medium when so initially here, so if I can show somewhere here I nu is much less than I s, and here I nu is greater than I s. That is why it starts saturating, the gain drops down, because gain coefficient is given by gamma of nu is equal to gamma 0 of nu into divided by 1 plus I nu by I z, I s, the saturation index. So, when I nu becomes greater than I s, in the denominator this term continuously increases 1 plus 2, 1 plus 3, 1 plus 4 and so on. That means the gain is continuously dropping down. If the gain is dropping down means the intensity, the rate at which the intensity is increasing is slowing down, and when the gain becomes, the gamma becomes 0, that is if I nu becomes much larger than I s, then gamma would tend to 0, that means the material no more provides any amplification, and we say that the gain is saturated. This is the concept of gain saturation, a very important concept of gain saturation, which is fundamental to steady state oscillations of lasers. As we will see later, that this is the fundamental concept, gain saturation is the fundamental concept which will lead to steady state oscillations of lasers. We will stop here, and in the next lecture we will take up the 4 level system, and we will see what is the advantage of a 4 level system over a 3 level system. So, practical lasers such as Nd:YAG laser and helium neon laser are 4 level lasers. We will discuss the laser systems towards the later part of the course, but in the next lecture we will discuss the physics of operation of a 4 level laser. Thank you.